Blocks on concrete, Jolly Rancher kids. I was talking back and now.
In this video, we'll start by reviewing something that you first learned about in Math 2A, the concept of an antiderivative. Antiderivatives are the focus of section 4.9 of Stewart's textbook. And what do you do in a first calculus course? Well, in a class like Math 2A, you learn how to take derivatives of lots of different functions. So remember that a derivative is measuring the instantaneous rate of change of a function. You learn how to start with a function and output a derivative. So maybe you start with the function f. You learn how to take the first derivative of f prime. And that's just another function. So you can take the derivative of that. And you differentiate, and you get the second derivative of f. And you differentiate, and you get the third derivative of f, and the fourth, and the fifth. Differentiation is a process where you put in a function, and you get out another function, the derivative, that measures the instantaneous rate of change of your original function. So what are antiderivatives all about? Well, the question is, can we go the other way? If you start with a function, how do you find another function whose derivative is the function you started with? So can we go this way? Can we go this way? Can we go this way? And this is a big part of what this course is all about. So let me start with a definition. Well, what is an antiderivative? This section is all about antiderivatives. What is an antiderivative? A function, capital F of x, is an antiderivative of a function, little f of x, if the derivative of capital F is equal to little f. So what is an antiderivative? The antiderivative of a function little f is some function capital F where you take the derivative and you get back the thing that you started with. Okay, so let me highlight one thing before I give the first example, which is it's very, very intentional that I said an antiderivative and not the antiderivative, and that's an issue that we'll come back to in a future video. Okay, so let's start with an example. Let's try to find an antiderivative of, well, what's the simplest function you can think of? How about the constant function little f of x equals 1? If you think about the examples of derivatives that you know, it won't be so hard to come up with the example of capital F of x equals x. Why is this an antiderivative of little f of x equals 1? Because what do we need to check? We need to check that the derivative of capital F, which is the derivative of the function f, equals 1, which is our function little f of x. So we see that capital F of x, take the derivative, you get little f of x. That means capital F is an antiderivative of little f. Let's do another example. So let's say find an antiderivative of the function little f of x equals x. Well, if you remember some basic things about derivatives, it's not hard to come up with the example of capital F of x equals 1/2 times x squared. So why? Because when you take the derivative of capital F, that's the derivative of 1/2 x squared derivative. And remember how the power rule works. The 2 in the exponent comes down by 1 and multiplies the outside of the function. So we get 2 times 1/2 times x to the 1, but this is just equal to x. And x is little f of x. So what have we seen? The derivative of capital F is equal to little f. So f of x equals 1/2 x squared is an antiderivative of little f of x equals x. Okay, we could do the same thing. And instead of starting with f of x equals 1, which is x to the 0 power, or f of x equals x, x to the 1 power, we could ask for an antiderivative of f of x equals x squared, or f of x equals x cubed. But let's just do them all at once and say, okay, in general, an antiderivative of little f of x equals x to the capital N power is capital F of x equals x to the n plus 1 power, but we want to divide by that n plus 1. Okay, why does this work? Because when you take the derivative of capital F of x, you get n plus 1 over n plus 1 times x to the n. Right, so this n plus 1 comes down, cancels out the 1 over n plus 1, and we get x to the n, which is x to the n, which is little f of x. And why does this work? Because of the power rule for differentiation. All right, so maybe you believe me when, like, n equals 0, we get x to the 0, we get 1 over 1 times x to the 1. Matches up with this formula exactly. F of x equals x to the 1, we get 1 over 2 times x to the 2. Matches up with this formula exactly. What if you had f of x equals x to the 1/2, like square root of x? Well, this would say we get 1 over 1 plus 1/2 times x to the 1 plus 1/2. And that's still okay, because remember, the power rule still works fine when your exponent is like a fraction, or even if it's something like pi. The derivative of x to the pi is pi times x to the pi minus 1. It's even okay when your exponent is negative. There's just one special case we need to consider that we'll come back to in a future video where this is not quite true, which is when n equals minus 1. So it's just not true that an antiderivative of x to the minus 1, which is 1 over x, is 1 over minus 1 plus 1 times x to the minus 1 plus 1, because that gives you 1 over 0, which doesn't work. Like, it's not defined. So this formula can't possibly be true when n equals minus 1, but in every other case, it's okay. So in the next video, we'll talk more about other antiderivatives that we can compute given what we know about taking derivatives.